Ladies and gentlemen, my name is Xiao-zheng. I'm from Institute of Oceanographic Instrumentation, Qilu University of Technology, Shandong. Academy of Sciences, Qingdao, China. The title of my thesis is Research on Obstacle Avoidance Tracking Planning of Hyper-Redundant Manipulator based on VR technology. Abstract. In order to ensure that the super-redundant manipulator can work without collision in the obstacle space, this paper designs an obstacle avoidance trajectory planning method for the super-redundant manipulator based on VR technology. The super-redundant manipulator with 7 degrees of freedom was selected as the research object. VR technology was introduced to construct the virtual model of the super-redundant manipulator, and the redundancy space of the manipulator was determined according to the model. Then, the pre-selected minimum distance index is selected as the obstacle avoidance index of the mechanical arm. Based on the calculated real-time minimum distance, the inverse kinematics equation of the mechanical arm is obtained by using the escape velocity dynamic obstacle avoidance algorithm, so as to realize the tracking planning of the obstacle avoidance trajectory of the super-redundant mechanical arm. Simulation experiment results show that it can be seen from the curve of the joint angle and angular velocity of the manipulator that the proposed method successfully avoided obstacles and reached the target configuration after the application of the proposed method, which met the requirements of the obstacle avoidance trajectory tracking planning of the current hyper-redundant manipulator, and fully proved the effectiveness of the proposed method. Introduction. As a kind of joint mechanical device simulating the human arm, the mechanical arm has developed into the supporting technology of modern high-end manufacturing industry, and has been widely used in many fields such as material welding, spraying, handling, cutting, and so on. Through the operation of the manipulator arm, not only the production efficiency and operation quality is improved, but also the existing labor environment is improved, so that it can gradually replace the manual operation in high-risk environment 1. With the continuous expansion of production requirements, the operating environment of manipulator in many application fields is no longer a relatively free space, but a constrained space formed by many obstacles. Therefore, the obstacle avoidance planning of manipulator has become one of the important research directions in the technical field of manipulator 2. 1. Taking the 7DOF hyper-redundant manipulator as the research object, the virtual model of the hyper-redundant manipulator was constructed by VR technology, and the redundant space of the manipulator was determined according to the constructed model. 2. The pre-selected minimum distance index was selected as the obstacle avoidance index of the manipulator, and the real-time minimum distance was calculated. Then, the inverse kinematics equation of the manipulator was established by using the escape velocity dynamic obstacle avoidance algorithm, so as to realize the tracking planning of the obstacle avoidance trajectory of the hyper-redundant manipulator. Research on tracking planning method of obstacle avoidance trajectory information of hyper-redundant manipulator. Introduction of VR technology. Due to the human participation, in the past, the accuracy of the obstacle avoidance trajectory planning process of super-redundant manipulator is very low, which only uses the naked eye to observe the target. It is high precision and inflexible to solve the problem by machine. According to the data given by the computer, the operator's operation mode combines the advantages of the two well, and VR technology can realize the good combination of the two. 3. In order to facilitate the operator to observe the video scene, the virtual model is drawn in wireframe mode, as shown in Figure 1. The video image is captured by the camera carried by the end of the manipulator. The virtual model represents the state that the manipulator moves to the target position accurately, that is, the state that the target and its mark point should move to when it can grab the position of the replaceable module 4. The camera used in this paper is the industrial camera produced by Point Grey Company. The model is FL2-03S2C. The resolution is 640-480. The lens is 09C industrial lens of computer company. The field of view is 32 degrees. Build a virtual model of the robotic arm. A 7-degree of freedom super-redundant manipulator is selected as the research object, which is composed of 7 joints, 2 end effectors, and 2 arm rods. Its structure is shown in Fig 2. The virtual model of the robotic arm is established according to the coordinate system of Fig 1, and the corresponding DH parameters are shown in Table 1. Table 1.dh parameter table of virtual model of robotic arm. Equation 1 represents the forward kinematics model of the robotic arm, and establishes the mapping relationship between the operating space and the joint space. From this formula, the pose transformation from the 7th coordinate system to the base coordinate system can be obtained. The core problem of hyper-redundant manipulator kinematics is inverse kinematics. Assuming the end pose, task space, joint space, of the hyper-redundant manipulator, there are 2. In formula, 2 represents the mapping function from joint space to task space, that is, the positive kinematics equation. Knowing the value of each joint variable, the pose of the end can be uniquely determined. When the end pose is known, solving the value of each joint variable is an inverse kinematics problem 6. The scholar Whitney first proposed the pseudo-inverse method to solve the inverse kinematics of the hyper-redundant manipulator. In essence, it is an optimization problem as follows. 3. Equation 3 shows that the norm of joint velocity should be minimized on the premise of minimum error of end tracking trajectory, so the solution obtained by pseudo-inverse method is also called minimum norm solution. The Lagrange multiplier method is used to solve the optimization problem of equation 3. 4. In equation 4, represents the pseudo-inverse of Jacobian matrix. Determine the redundant space of manipulator. The redundancy space of the robot arm greatly affects the accuracy of obstacle avoidance trajectory tracking planning. Therefore, the determination of the redundancy space of the robot arm is studied in this paper. The above process completes the determination of the redundant space of the manipulator, which lays the foundation for the trajectory tracking planning of the manipulator. The obstacle avoidance index of manipulator is selected. The selection of obstacle avoidance indicators will directly affect the effectiveness of obstacle avoidance. Especially for dynamic obstacle avoidance, the random movement of obstacles, choosing a reasonable index that can accurately and quickly describe the position relationship between the obstacle and the manipulator is particularly important for ensuring the real-time nature of obstacle avoidance planning. In view of the above problems, this paper preselects the minimum distance index, and its idea is to establish corresponding bounding boxes for different manipulator configurations, use intersection test, eliminate other safety members before calculating the real-time distance, only consider the position relationship between the colliding members and obstacles, and calculate the distance value in the local coordinate system of the members, as shown in Fig 3. During the movement of the manipulator arm, if the distance between each connecting rod and the obstacle is greater than the threshold distance, the position and posture of the manipulator arm can be obtained without changing the minimum norm solution, pseudo-inverse solution. On the contrary, the null space vector should be used to adjust the posture of the manipulator without changing the terminal posture, so as to meet the condition of no obstacles. Therefore, there are two basic requirements for obstacle avoidance trajectory tracking planning of super-redundant manipulator. The first is to meet the terminal motion requirements, and the second is to avoid moving obstacles 10 to 11, namely. In order to reduce the influence of rank changes and maintain the continuity of joint speed, the obstacle avoidance gain and the escape speed are introduced. The dynamic obstacle avoidance inverse kinematics of the escape speed is expressed as A. The ground experimental system of the hyper-redundant manipulator is an important part of the development process of the hyper-redundant manipulator. The ground experimental system based on the hyper-redundant manipulator can simulate a weightless environment, verify the validity of the theory related to the hyper-redundant manipulator, and test the performance and function of the manipulator. In the experimental system, 1. Air flotation platform. In order to simulate the microgravity environment in space, this experimental platform is based on the air flotation method, using the jet reaction force of the air bearing to support the 7 degree of freedom super-redundant manipulator on a flat and smooth marble platform. Counteract the effects of gravity. The air pump is used as the air source to supply air for each air foot to support the robotic arm to simulate a microgravity environment. 2. Central controller. 3. Ground inspection equipment. 4. Simulation notebook. 5. Console. Although the 3, 4, and 5 joints of the hyper-redundant manipulator can move within the range of -270 degree, due to the limited area of the air bearing table and the restriction of the air foot support mechanism attached to the manipulator, the range of motion of the robotic arm on the experimental platform is limited. In the experiment, the range of motion of joint 3-165 degree, 90 degree, the range of motion of joint 4-120 degrees, 120 degrees, the range of motion of joint 5-20 degree, 165 degree, the joints of joints 3, 4, and 5 the speed cannot exceed 2 degrees/s, and the absolute position accuracy of the end is less than or equal to 10 millimeters. Through the simulation experiment, the change curve of joint angle and velocity in the process of obstacle avoidance movement of super-redundant manipulator is obtained, as shown in Fig. 4. Can be seen from the Fig. 4, 3, 4, 5 joints angle and angular velocity are within the scope of the constraints, and a smooth curve can be used for the control of mechanical arm. Arms successfully avoid the obstacles and reach the target configuration. Today's hyper-redundant manipulator trajectory tracking of obstacle avoidance planning requirements fully demonstrates the effectiveness of the proposed design method. On this basis, the traditional trajectory tracking planning method based on machine vision technology is compared and further verified from the perspective of timeliness of response of tracking planning instructions. The results are shown in Figure 5. According to Figure 5, with the increase of verification times, the response time of tracking planning instructions of different methods is also changing constantly. However, it is obvious that the time of the proposed method is lower than that of the traditional method. It can be seen that the method presented in this paper can realize trajectory tracking planning more quickly. Conclusion. In this study, VR technology was applied to the obstacle avoidance trajectory tracking planning of hyper-redundant manipulator. In the design process, the hyper-redundant manipulator is taken as the research object. The virtual model of the hyper-redundant manipulator is constructed by using VR technology, and the redundant space of the manipulator is determined. Then, the pre-selected minimum distance index was selected as the obstacle avoidance index of the manipulator. According to the calculated real-time minimum distance, the inverse kinematics equation of the manipulator was obtained by using the escape velocity dynamic obstacle avoidance algorithm, so as to realize the trajectory tracking planning. The experimental results show that this method can effectively meet the requirements of obstacle avoidance trajectory tracking planning for hyper-redundant manipulators and is suitable for extensive application. In the following research, the proposed method will be further optimized from the perspective of improving the control accuracy.